and we're going to head right into the second session, to the third session, because we're right on time. So please welcome Mark, who's going to tell us about embedded development. Hey, Mark, how are you doing?
Hi, how's it going?
Good.
All
I'm glad
right,
that we are on time. So take it
great.
away.
And it looks like things are working, sharing the screen and stuff, so I can get going. Yeah, so my name's Mark Goodner. I'm a program manager on the C++ team here at Microsoft, and I'm here today to talk about Visual Studio and VS Code using those for embedded development. So just kind of to go through what I'm going to talk to you about is kind of why we're looking at embedded developers, or why we're working to improve Visual Studio and VS Code for embedded developers, the approach we're taking, where we're at today. Then I'm going to give you a quick demo of using, I'm going to show VS Code today, of doing some embedded development with that, so live demo. And then I'll talk a little bit about what's next, and then we'll have time for some questions, hopefully. So just as kind of a preview to show you where we're going, this is a screenshot of Visual Studio with most of the embedded features lit up. So you can see there's a peripheral register view there. Down at the bottom, there's a view of RTOS threads. So we've got RTOS awareness. And kind of the same view in VS Code. So we're trying to maintain parity between VS and VS Code of the features that we're enabling for embedded developers. So why do we care about embedded developers? One of the big reasons is actually Azure RTOS. This was a product previously known as ThreadX. You'll still see it referred to as ThreadX a lot. But this is a real-time operating system that that Microsoft provides for microcontrollers. So we previously didn't have something this low level, but now that we have something that's low level that runs like on Cortex-M processors, we need to be able to provide a end-to-end developer experience across our own tools, because a lot of embedded development occurs outside of Visual Studio and VS Code. There's a lot of proprietary IDEs out there, or vendor-specific IDEs or tool sets. But with ThreadX, having Azure RTOS as a Microsoft first-party experience, we wanted to be able to give a first-party story across our development environments, and full support for those. Another reason we care about embedded developers is they're a very large C++ cohort. So there's a lot of embedded developers out there that use C, C++, and it's kind of one of the last markets we haven't really spent time on in our C++ support for Visual Studio and VS Code. And they have unique core inner loop needs. The embedded developers, the needs that they have for their development in terms of like edit, build, deploy, debug are different, because they're really working close to the hardware. So their needs, there's a lot of the core standard C++ functionality of VS and VS Code accrues to these scenarios, but we need to do more for embedded developers so that they have a good working environment. There's also some interesting problems embedded developers have. The acquisition is really painful for embedded developers especially. It's a common pain point across C++ that it's difficult to get your tool sets set up and all of the libraries and everything that you need. But for embedded developers, it's especially hard because there's cross compilers. The cross compiler is often set for a specific piece of silicon. You have to go to a specific place to go find it, all of these sort of things. So we wanted to try and take a try at trying to solve some of those problems. So how are we approaching this? The first is we're trying to commonly solve those core inner loop needs across VS and VS Code. This is kind of a internal point to us, but you'll see it reflected in when we talk about VS or VS Code. You'll see a lot of the same functionality. It'll look the same, and that's because for us, we're trying to write once as much as possible and have it working in both environments. And so, today we're focused on some of the core needs for embedded developers in that inner loop. And one of those is peripheral registers, being able to access things like the GPIOs on the device, on the microcontroller, and being able to see what those values are, interact with those values, having a semantic representation of those. This is something that's not as common for desktop developers, but microcontroller developers really need that. We also are providing a view for RTOS objects. So for ThreadX and also for FreeRTOS, we're giving a view of what those objects look like. This because an RTOS gives you an ability to manage tasks across the RTOS in a way that kind of virtualizes threads, even though you may only have one thread available on the microcontroller. But you want to see the representation of all of the tasks running in the RTOS and see what their states and values are. So And in terms of acquisition, we're really trying to solve acquisition not only for the IDE, but also for CI, because you need a reproducible build environment for your projects, of course. And that should work for your IDE and it should work for CI. So what we've done is we've added artifact capabilities to VC package. This is an ability to express, I need ARM GCC, I need an OpenOCD debugger, these sort of things that get described in a manifest that you can check in with your project. And then that will pull down the bits if you don't have them, put them on the command line and make them available for use. And we'll see more of that in the demo. And the other thing we're working on, and I don't have a lot to dive into in depth here, but we're working closely with silicon vendors. We really, in order to be successful here, we really need silicon vendors to be able to recommend the VS family of IDEs to their customers. Otherwise, their customers won't hear about this. And so we're working on with them as well through adoption of VC package so that there would be registries available of the tools that come from the silicon vendors available to embedded developers to use in their solutions. And then, of course, we've also got to work with the silicon vendors around how can we, in the future, start defining new project experiences that include the device configurations that are necessary for embedded development. And so where we're at today, we have a peripheral register view that we're going to show, and we have an RTOS object view for Azure RTOS and for free RTOS. I'll talk at the end about where we're going next because we have more coming on that. And then we also have some example projects already pre-configured for you for Azure RTOS. These include the debug configurations and VC package manifests, so you can see how all of this works together. We have one for an Azure IoT dev kit, which I'll be showing today, which is kind of a sample dev board, this little credit card guy that has sensors and stuff on it for use. And then we also have one for NXP and for STMicro. If you can take a look at the configurations for these and kind of see how those are set up, I'll walk through a little bit of that in the demo and adjust it to your own needs. And then the other thing our team did last summer, we had an intern on our team who worked with the WSL team and an open source project to bring USB IP support to WSL2. That enables you to share your microcontroller from your Windows host machine into WSL, and I'll be trying to use that today. And so in terms of setting up for Visual Studio, when you install Visual Studio, our embedded capabilities were introduced in 17.1. And in order to use them, just install the Linux and embedded development workload. And the options for that are pre-selected, the embedded IoT tools right there. And for VS Code, search for the embedded tools extension. That will pull in all the other necessary dependencies that we have, like the C++ extension in VS Code. All right, so let's do it. Let's try and take a look at what this is going to look like. This is how easy it's going to be to get an embedded project going. But first, I want to go to my administrator window here. And what I want to do is show you USB IP. So USB IP is a utility here that I can actually share a USB device over USB IP and then connect to it from a USB IP client. And that's how we're bridging from the Windows host into WSL. And so what I can do is take a look at what's on my machine. And you can see here, the one I'm interested in is this ST-Link debug. This is my little dev board that I showed earlier. And this program has a helper function, WSL attach, because in order to share something with USB IP, there's a lot of commands you have to run on the client side as well on the host side. And this command automates kind of on the receiving side because WSL is local on my system. So we can just run this command and attach it in there. And I can show you this is my WSL system. You can see there's only the root USB hubs represented there. But if I run this command, then what's happened now is if I run lsusb again, now this device is shared into my WSL environment. And if I do the list again, you can actually see that it shows that this device is attached. So let's go to our Getting Started project. So this is a GitHub project that I cloned. Links are in the deck. And what this project has in it, this is a pretty basic project for a ThreadX project. So I've got my source code, I've got my CMake set up, but I have this VC package configuration file. And so if I take a look at this file, what you'll see is that there's a registry. All that's at this registry is JSON files that describe the artifacts that are available. And so here I've specified that I need ARMGCC, I need OpenOCD, I need CMake and Ninja to build my project. And so the registry doesn't contain the bits. The registry contains metadata that says where to go get those from. So when I use this, it's going to go get the compilers from ARM, it's going to go get the OpenOCD from our build, etc. And so if I say CMake version right now, you'll see I don't have CMake on the command line. But what I can do now is just source VC package. So this is a .source script. So now I've got VC package available on the command line. And all I have to do is say VC package activate. And this command is going to read that manifest file. And if I don't have these tools installed, it will go get them, pull them down, and put them on my system, and then activate them for use. So now you can see that all of these tools, it went quickly because I've already installed these before. But now if I run CMake version again, you'll see that I've actually got 320 available on my command line. So now from this activated environment, I can start VS Code. Give this a little bit more room here. And so now this is coming up, and now my project is activated. I've got my compilers available to me for the for ARMGCC, and IntelliSense is working. So if I can search for button, you can see now I can actually navigate down here to a callback for pressing a button on the board. I've got a breakpoint set here on this line. You can see IntelliSense, hovering over this value shows me that this expands to a register. So this TEM3-CCCR1, this is a peripheral register. And so what I want to show you is how I can actually inspect that and see that value working. And so let's see, now I can go ahead and launch this. And so this is running in the WSL context. You can see here that WSL is set, but it's actually reaching out to the device over USB IP that's actually connected to my Windows host computer. And what it's doing now, it's flashing the device. And so you can see on entry, we break, and that actually pulls up our assembly file that's part of this project. So this is our startup assembly file that's very common within embedded projects for your startup. And I can go ahead and step around through this. I can also, from the call stack, I can right-click and open a disassembly view. And so I can even step my disassembly. So this is pretty great. These are pretty common tasks for embedded developers to need to go down to this level. It looks like I've got some rendering issues from the screen size I've got here. But let's go ahead and continue. Now I have a breakpoint set there, and if I press the button on the board, that's going to trigger my breakpoint. And it's hard to see here because it looks like I've got some rendering errors with the size that I have. Let me see if I can shrink this down a little bit. There we go. All right, so if I scroll down and I find this TEM3, this is the general purpose timer register that we were looking for. And then we can see CCR1 was what this is set to. And so now if I step over this, you'll see that that value updated. So this is useful to embedded developers because often they need to check what's going on the peripherals attached to the hardware and making sure that their code is doing the things that they expect the code to be doing. Another thing within embedded development that's interesting is hardware breakpoints. So you don't have infinite hardware breakpoints. So we've got 4 or 5 breakpoints set now. Now I've got 6. Now I've got 7. And you'll notice that this one set is gray. That one set is gray because we only have so many breakpoints available to us on this board. And so what would happen if I didn't respect the number of hardware breakpoints on the board is I would try setting another breakpoint, and then it could corrupt the state of the debugger. So we actually have support for monitoring that so that you can unselect another breakpoint and then set the one that you wanted. So that's another useful thing that we've got. And before I forget, here's our RTOS viewer. And here you can see all of the tasks that are running as part of the RTOS. And you can see things like, how many times these tasks have run, where the stack pointer is, where the stack ends, what the stack size is, and also what the maximum usage on this stack was. This view changes a little bit from RTOS to RTOS. This is what it looks like for For ThreadX, for free RTOS, it would look a little bit different based on the values that are available. And so I'm going to go ahead and stop debugging. And if I show you one other thing here, in this folder in the launch.json, you can see this is our configuration that we were using to launch. And you can see here that we're configured for, we're just running on the command line for our ARM-GDB debugger, but the important part is here is the debug server path and server args. This is something that varies depending on whether or not you're using OpenOCD or Segar. We have Segar examples for our NXP board, and then the parameters that you pass for your specific board. And so this is something that's going to vary board to board in terms of what you need to pass in order for your specific board. And here's the hardware breakpoints that I mentioned. So this particular board has a limit of 6, but that also varies board to board. So let's get back to the presentation. All right, so that's it in a nutshell. You can just clone a repo down, go into your repo. I didn't show the install of VC package because I already had it installed, but we have a one-line installer for VC package. That's what it looks like on Windows. And then once you have VC package available, then you can just say VC package activate when you have a manifest. And it will pull down everything that's necessary for the project if it's not already there, and then activate it for use. And then you can launch VS Code, or from a VS Code or Visual Studio command prompt, I should say, you can start dev-env, and everything's available to you, and you've got a complete bootstrap Linux and complete embedded environment available to you. That's the one-liner for Linux, that's PowerShell, and that's command. All right. And just kind of for reference, as a reminder, if you ever find these presentations, this is kind of an example of what the manifest looks like. And just kind of in review, this is the peripheral register view. This is the screenshot from VS Code of the before and after of stepping that value. And then we've got our RTOS object view. This is what it looks like in Visual Studio. So very similar view, but themed for Visual Studio, using Visual Studio functionality to get the same view there. So in review, we've got our core inner loop set up for embedded development for edit and build. We can debug on a device target. We have peripheral register view available now, and RTOS object view. And we're setting up our reproducible environments through VC package. And where we're going next, we're continuing to work on partnerships. I hope that there could be something more public to say about that, hopefully around Embedded World, which would be in late June. And we're continuing to make improvements here. So continuing to focus on our WSL support. This is something, the demo I just showed you, using our extension in WSL doesn't work with the release version today. We have an RC that's posted on our GitHub that you can download that has the WSL support as part of it. That RC also has Zephyr support, so we've already gone further to add another RTOS view support for Zephyr. And one of the next places we're going, not part of our RC, but we're also working towards getting VC package integrated as part of Visual Studio and part of Visual Studio Code, so that you don't have to activate from the command line and then launch your IDE. Instead, we'll have, when that manifest is there, just activate within the context of the IDE. We're also working on a serial monitor. The word monitor is there, but it does support input. So that's something that you'll see in Visual Studio 17.3 when that first preview comes out soon. And then we're also working with CMSys. So we're hoping to start leveraging CMSys to get things like the SVD file for rendering the peripheral views, helping us to understand how to automatically configure for debug and all of those sort of things. Don't have a lot of time to go into this, but I didn't talk about makers at all. Our team actually does own the Arduino extension that's available for VS Code. It's not a deep area of focus for us, but it is something that we do care about, and we do keep this extension current. I don't know a whole lot about where we're going to be going for the future of this, because we're more focused on professional embedded scenarios around RTOSs right now. But we're also looking at the Raspberry Pi Pico. We've been doing some experiments on getting the Raspberry Pi Pico SDK to work within the context of VC package, so that's something that should be coming soon. And then we can probably freeze this slide or take a screenshot of this. This is a link to all of the announcements on the C++ blog about the capabilities that I've shown. And that's my contact information if you would like to reach out and learn more. And I think that's the end of the deck there. Let's see. Oh, I went really fast.
Yeah, thanks very much. Don't worry about it. So we've got a couple, well, one comment and one more of a comment and one question. One question is Azure RTOS C or C++?
I believe it's C. I always say C++, but the embedded world is largely C.
Cool. And then the more of a comment is, in my opinion, for embedded development, VS needs a piece of software which can be connected to and read from embedded system and read from embedded systems automatically. Get the VS Code could have some extensions for this, but at some point you wonder if there's too many extensions to the point that becomes difficult and out of your way to work with VS Code and not another piece of software. What are your thoughts on that?
I don't know how to think about that one. That's almost kind of a difference between Visual Studio and VS Code, I think. VS Code is really built to, all of the capabilities come from extensions. It's unlikely that we would take and put all of this core functionality just directly into VS Code with no optionality. There's ways that you can express extension dependencies as part of metadata that go with your project for VS Code, particularly with dev containers. For Visual Studio, that's much more the case in Visual Studio that things are all there. You select your installation options and then you get things as part of the install. And so the embedded workload in Visual Studio is something that we're intentionally not delivering as an extension. It's actually part of Visual Studio.
Cool. Feel free for other folks to drop questions in the public chat. We've still got a decent amount of time. So you mentioned Arduino and Raspberry Pi. So
yeah,
like my kid has been interested in some coding things. Do you think Visual Studio Code with the Raspberry Pi is like a nice experience to get going with something like that?
Yeah, so VS Code, actually, you can run that on a Raspberry Pi. The thing we're looking at with the Raspberry Pi Pico SDK I mentioned is the Raspberry Pi Pico is a little microcontroller from Raspberry Pi. It's not the full, single board computer that is the regular Raspberry Pi. And their SDK is a little bit difficult to bootstrap and get running. It's not too bad on Linux, but particularly on Windows, it's a little bit more painful. So this is something where the acquisition strategy from VC Package can help, because we can just express that dependency, pull that SDK down from Git, and then have all of the other system dependencies expressed as part of a manifest, so that you don't have to go through the manual and go through like 5 or 6 pages of just setting up installation options before you can get going. Yeah. And
I wonder if that would be useful for, like, on my desk, I've got a Synology NAS, which runs NatMailchimp, and like I've cross-compiled things for that myself by just pulling down the GCC toolchain and sometimes completely hacking something to get it working. But do you think that like VC package artifacts and VS Code would be a nice thing for targeting a system
I think
like
so.
that?
VC package artifacts is going to go a long way to helping with cross-compile scenarios like that. I mean, that's really kind of the core place that we started with the artifact work. I mean, we're expanding the artifact work to cover C++ more generally. So we're working on being able to activate MSVC via VC package, for example. So the scenarios there, we care about desktop, and we'll be expanding that to cover desktop scenarios as well.
Cool. Yeah, that sounds good. Anything to make that easier. Like I remember trying to compile Nginx with their RTMP module for my NAS, and the whole experience was not very fun.
Yeah.
Cool. Well, thank you very much. I guess we'll see you later, Mark, and we'll
absolutely
move on to the next session.